Hi, how you going? Mr. Bennett here. Today we're going to be looking at Newton's second law of motion. Alright, so really important law. Certainly when we start looking at car safety, it's a very important law. So if you think about Newton's first law, when we talked about having zero force, that implied we have constant velocity. Alright, so either the object's moving in a straight line at constant velocity or it's stationary. Now, the definition of acceleration that we've used in the past is acceleration's a change in velocity over time, isn't it? So, from these two results we have the information. So we have a net force. So if our net force is not zero, that implies that our velocity mustn't be constant, and therefore it implies an object must accelerate. Alright, so that sort of matches what we thought from the law of inertia. So what it says though, if we have a net force, the larger the net force, then the greater the acceleration. So if we double the force, then we double the acceleration. We triple the force, we triple the acceleration. Halve the force, we halve the acceleration. Alright, so acceleration obviously has a direct proportionality to acceleration. So we could say force and acceleration are directly proportional to each other, and we'll talk about that definition in class. So check yourself. So if you're pushing a crate with a net force of 100 newtons and the frictional force is 100 newtons, does the crate move? Does it accelerate? And the answer is no, because the net force is in fact zero. Alright, so does this mean the crate is not moving? No, just the velocity is constant, and in fact the velocity is zero. Alright, so now push with 150 newtons of force. Okay, I've still got the friction of 100 newtons. So does the crate accelerate? And the answer is yes, because now we've got a force of 50 newtons. So you now get a friend to come and help you push at 150 newtons as well. So by how much does the acceleration increase? Well, you're now going to have 300 newtons of force pushing, you're going to have 100 newtons of friction stopping, so now you're going to have 200 newtons of force pushing. So that's 4 times larger the acceleration, so it increases by a factor of 4. Now, we've talked about this I think already, but mass is the quantity of matter in an object, alright, and so the weight is the force of gravity on the object. So mass is a universal property, and weight depends on the gravitational field. So we talked about Earth. If you're 120, I think it's 1/5 or 1/6. It is 1/6. So you're 120 pounds or kilograms. On the moon, you'll weigh 20 kilograms. So a really good weight loss property? No. Alright, you still have a mass of 120 kilograms. Alright, so only your weight that's changing. Alright, so the difference between those terms is quite often misunderstood. And if you think about it in terms of if you go shopping, quite often we look for the weight of an object, but we should be looking for the mass. So that word weight is really used inappropriately a lot of the time. But on Earth, our mass and our weight is pretty well the same. Alright, so mass is the measure of inertia. Alright, so its metric unit is in fact kilograms for mass. The metric unit for weight is in fact newtons. Alright, but if you go shopping, you'll see things written in grams or kilograms. Technically, they should be, using the other term. So, if we look at this demonstration, this is to do with the law of inertia. Alright, so if a nail is hammered in a piece of wood, so let's say you have quite a heavy lot of books there. Right, it's got a lot of inertia. When you hit that, the force, right, you're going to have to hit it with the same force as, depending if there's one book or no books. Because it's got a lot of inertia there, you'll find that the person underneath the books is really not going to feel the the nail being hit, right? Because it's really hard to move all those books. So therefore, not a problem. So if we start talking about that, the force, right, if we have a greater mass, then we have a smaller acceleration. So if we double the mass, that implies we halve the acceleration. If we triple the mass, then we have 1/3 of the acceleration. Right? If we halve the mass, then we double the acceleration. So we say that the mass and the acceleration are inverses of each other. So they're inversely proportional to each other, and we'll talk about that also in class. So if we have a hand accelerating a brick where no friction's occurring, so if we accelerate 2 bricks, what's that going to do to the acceleration? Well, 2 bricks will weigh twice as much, we'll have half as much acceleration. If it's 3 bricks, that's 3 times the mass, then we'll have a third of the acceleration. Right? If we have twice as much force on 1 brick, then we'll double the acceleration. If we have twice as much force on twice the mass, then we'll have the same acceleration. So I think that should make sense with that. So acceleration is equal to the net force divided by the mass, and the acceleration is always in the direction of the net force. Okay, so if we push on the top pedal here, what's going to happen to the bike? Well, we've all been on little tricycles. Okay, we are going to go forwards, aren't we? If we push on the bottom pedal, then the bike's not going to move at all, is it? Because it's not going to allow that to actually provide a force on the wheels. So weight on Earth, right? So obviously the connection is if you weigh 1 kilogram on Earth, then the acceleration is in fact gravity, 10 meters per second, so therefore 1 kilogram is equal to 10 newtons of force. So here's a little example. So if we're carrying a bowling ball in a shopping bag, so how much weight does the bag support? Well, the weight is equal to 6 kilograms times by 10, which is the acceleration, so it's 60 newtons worth of force. Now, if the lady quickly yanks that bag upwards at 5 meters per second, what additional force is required by the bag to support the ball? Well, we know that 6 times by 5 is 30, 30 plus 60 is 90, so that bag now needs to support 90 newtons of force. Alright, so example. Now, here is the tension on an elevator cable. So let's say the elevator just stationary, no acceleration. If the cable, if the lift weighed 1 kilogram, then there'd be 10 newtons of force on it. 5 meters per second upward. Okay, so we've got that 1 kilogram there. So if we accelerate upwards, what's that going to do? Well, that's going to actually increase. Alright, it's going to increase the force there to 15 newtons. Okay, coming downwards, it's in the same direction of the acceleration downwards. So therefore, that's going to reduce the force there. And if this is in free fall, then there's going to be no force on the elevator cable. Right, so here's another little explanation to explain why objects fall at the same rate no matter what happens in terms of their mass. So the ratio of their weight or mass always stays the same, right? So the weight, since the weight depends on the mass. So if we've got that there, the mass, we've got the same force, we've got double the force on double the mass, so therefore that's why these objects will fall at the same rate. Alright, the only thing that's going to affect it is the ratio of the surface area, okay, and that's assuming that we have frictional forces applied. Now I can probably show you this demonstration in the laboratory. We've got one of these cubes, so I'll do that in class. Here's a little video from YouTube that you might like.
Well, in my left hand I have a feather, in my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time. How about that? That proves that Mr. Galileo was correct in his findings.
Alright, so really cool little demonstration. So you can do the same thing. Obviously, when we start talking about air resistance affecting things, obviously if you drop a book and drop a piece of paper, then that's going to show how air resistance does really affect that. Alright, so friction and air resistance are sort of forces that really oppose motion, and what we have to do is we need to possibly consider those in real life, but in a lot of the stuff that we do in physics we will ignore those forces. Origin of friction on the molecule, we'll just skip through that. And just want to show you this little example here about a golf ball and a ping pong ball. They have roughly the same sort of size, but they have different masses. So the golf ball has a greater weight. The two balls have the same size. The drag force is equal. So same size and same speed. Which ball falls faster? Well, the golf ball falls faster because the net force is greater on that particular ball. So we've got drag and weight happening there that affect the motion of that. Now, obviously, if there's no drag, no frictional forces, then both those balls will fall at the same speed. Now, when we start talking about terminal velocity, obviously the thing that comes to mind is parachuting. So the speed of falling object increases until the drag force balances out. So when you're jumping out of a plane, depending on your surface area as to what your terminal velocity will be. Now, obviously the air resistance is pushing you up, your weight's pulling you down. Okay, so that's essentially how a parachute actually works. Now,